Respected dignitaries, esteemed faculty members, and my dear all friends, I am Tejashree from Triple Department. So today I am going to talk about homogeneous equations in engineering. So let's get into it. Introduction to homogeneous equations in engineering. Homogeneous equations are a class of differential equations that are essential in various engineering applications. They often describe systems where the output is directly proportional to the input or initial conditions. Understanding their properties helps engineers analyze and design systems more effectively. So, before getting into it, let's have a word. So, mathematics play a fundamental role in engineering, and one of the most powerful tools we use to model real world systems is differential equations. Among them, homogeneous equations are especially important because they help us understand how systems behave naturally without any external influence. For example, how a current decays in a circuit after switching off power, how a vibrating system slows down over time, how temperature reduces naturally, all these modeled using in homogeneous equations. Basic concept of homogeneous equations. A homogeneous equation, a differential equation, is an equation in which all terms contain the dependent variable or its derivative and the equation is equal to 0. So standard form is a n d power n y by d power d x power n plus a n minus 1 d power n minus 1 y by d power x power n minus 1 and so on to a naught y is equal to 0. No independent forcing term describes natural response of system. Solution depends only on initial conditions. So, in engineering terms, homogeneous equations represent a system where external energy or input is absent. Only stored energy or internal factors act. So, for example, d square y by dx square plus 3 dy by dx plus 2y is equal to 0. This equation describes a system that naturally settles down over time. To solve homogeneous equations, we use auxiliary or characteristic equation method where assumption method y is equal to e power mx. Substitution method, this converts the differential equation into algebraic equation. So we write m square plus 3m plus 2. So we should solve the characteristic equation and write the general solution. If that is equation, we write C1 e power m1x plus C2 e power m2x and so on. So both the terms decrease over time. System is stable. Response dies out gradually. Types of roots and their meanings. The nature of solution depends on roots of characteristic equation. Distinct real roots y is equal to c1 e power m1x plus c2 e power m2x. System response, poor decay or growth, no oscillation. Repeated roots. If the roots are repeated, we write C1 plus C2x into e power mx. System response. Slightly slower decay appears in critically damped systems. Complex roots. Y is equal to e power alpha x C1 cos beta x plus C2 cos. Sorry, so y is equal to c1 alpha x e power alpha x into c1 alpha cos beta x c2 sin beta x. System response, oscillatory behavior seen in vibrations and AC circuits. So engineering applications. Now let's explore homogeneous equations are applied in different engineering fields. Electrical engineering, RL circuit. When power is removed, L di by dt plus Ri is equal to 0. Solution, the current decreases exponentially. RC circuit, capacitor discharge, dV by dt plus 1 by plus V by RC is equal to 0. Used in timers, filters, signal processing. Mechanical engineering or vibration. Spring mass damper system. M d square x by dt square plus c dx by dt plus kx is equal to 0. M is equal to mass, c is equal to damping, k is equal to stiffness. Underdamped oscillates. Critically damped fastest return to equilibrium. Overdamped slow return. So this is used in car suspension systems, machinery, vibration control, etc. Thermal engineering, cooling of body. dt by dt, where T is temperature, by dt, where here T is time, is equal to kT is equal to 0. Hot object cooling in a room. Used to analyze stability, system response. If solution decays, system is stable. If grows, system is unstable. So, homogeneous equations are important because they describe natural behavior of systems, helped in designing stable systems, predict decay and oscillation. From the base for solving non-homogeneous equations. Real life understanding. The think of a swing. If you push non-homogeneous, if you stop pushing homogeneous, the swing only stops due to internal forces. This is exactly what homogeneous equation describes. So let's get into the presentation. Definition of homogeneous equations. A differential equation is homogeneous if it can be expressed such that all terms of the same degree, or if it can be written in a specific form. For linear equations, homogeneity means the equation equals to 0 when the input function is 0. Non-linear homogeneous equations have a different structure but still exhibit proportionality in their solutions. Types of homogeneous equations. Homogeneous differential equations are classified into linear and non-linear types. Linear homogeneous equations have solutions that can be superimposed to find general solutions. Non-linear homogeneous equations often require special methods for their solutions due to their complexity. So here we have the picture. You can see this non-homogeneous equations assumption. So y is equal to L of y is equal to y double dash plus p of t y dash plus q of t y is equal to g of t, where g of t is not equal to 0. P of t and q of t are continuous for all t in the domain. Now consider the homogeneous equation y double dash plus p of t y dash plus q of t y is equal to 0. If we consider only difference between the equations as their end result g of t, we can claim homogeneous linear differential equation. So these are equations where the sum of derivatives multiplied by the functions equal to 0. Their solutions can often be found using characteristic equation or substitution methods. Homogeneous non-linear differential equation. These equations involve non-linear functions of an unknown function and its derivatives. They are characterized by the property that if you multiply a solution by the constant, the result is also a solution. Solving them typically eh, involves substitution techniques or special transformations. Homogeneous equations can model many physical phenomena such as heat transfer, vibration, fluid flow, etc. And they help in understanding system stability, resonance, and response behavior. Engineering use these equations to develop control systems, signal processing, and structural analysis. Methods of solving homogeneous equations. Separation of variable is often used for solving linear homogeneous equations with certain forms. Power series and transformation techniques are also valuable tools for complex nonlinear cases. Examples for applications of engineering. Engineering applications. Homogeneous equations describe the vibrational modes of mechanical structures. They are used in electrical engineering to analyze circuit responses. These equations also appear in modeling, thermal processes, and wave propagation. Homogeneous equations. For differential equations which is not separable, we can try to study its homogeneity. A function f of xy is said to be homogeneous of degree n in x and y if and only if f of lambda x comma lambda y is equal to lambda power n f of xy. Homogeneous equation. A homogeneous function of degree 0 is said to be a homogeneous equation. Challenges and considerations. Non-linear homogeneous equations can be difficult to solve analytically and may require numerical approaches. Boundary and initial conditions significantly influence the solution process. Understanding the physical context is crucial for selecting appropriate methods and interpreting solutions. So, conclusion and summary. Homogeneous equations are the fundamental in modeling many engineering systems and phenomena. Recognizing their form and properties allow for effective solution strategies. Mastery of these equations enhances engineering ability to analyze, design, and optimize engineering solutions. So, let's have a final word. To conclude, homogeneous equations are fundamental concept in engineering that help us understand how systems behave naturally without any external inputs. They are widely used in electrical circuits, mechanical systems, thermal processes, control engineering. Understanding them allows engineering to design efficient and stable systems. Thank you for your attention. I would be happy for if any questions is asked. And thank you for watching. We are grateful for your interest and hope you enjoyed the presentation. Thank you.